Hello, this is Mrs. Schroeder, and we are still in Chapter 12, Section 3, talking about molecular composition of gases. Today, though, we're going to talk about something different, and we're going to start covering Dalton's Law. This is something we haven't discussed before. Dalton's Law of partial pressures. We'll cover that today. It relates how gas behavior and chemical formulas, partial pressures, behave in gases. So Dalton's law of partial pressures, again, this is a picture of a gas pressure gauge. Here's a couple of questions to get you thinking. The balloon is filled with pure oxygen. What's the pressure of the oxygen in the balloon? If a windbag is blown up with exhaled air, what's the pressure of oxygen in the bag? And if a solid container is filled with pure oxygen, what is the pressure in the container? So these are the things I want you to think about, and we'll see if you can answer those in class tomorrow. So in 1805, John Dalton figured out that if you take a mixture of gases, each gas will exert a certain pressure, as if it was alone. Again, we're imagining that gases are ideal gases. They're bouncing around. There's nothing else. They're not sticking to each other. They're not attracted to each other. So each gas is independent of each other. So John Dalton figured out that the pressure of each gas, he said, is a partial pressure. That's the pressure of that gas in the mixture. And he came up with a really nice, simple equation that says that the total pressure of the mixture is the partial pressure of each of the gases in the mixture. If there's two gases, A and B would just be pressure of A plus pressure of B. If there's 5 gases, it's pressure of each one of those. If there's 3, pressure A plus pressure B plus pressure C, as many as you need to figure out how many gases are in there. And that's Dalton's law. So, as an example, if I have my oxygen here, has pressure 1. Nitrogen is at pressure 2. What's the total volume, or the total pressure, if all of these gases were combined into one container? Well, pressure total would be pressure 1 plus pressure 2. So if this one was 5 and this one was 15, the total pressure would be 5 plus 15 would be 20. So according to the kinetic molecular theory, at the same temperature, molecules of different gases all have the same kinetic energy. This is why it doesn't matter what the molecules are. They all have the same energy. If they have the same energy, they'll collide with the same force. And remember that pressure results from collisions. So if all those collisions are happening with the same force, because we have the same temperature, it won't matter if it's oxygen or helium or argon or anything else. It's the same pressure from that gas. So the partial pressure. So quick practice for you. If I have 1 liter of nitrogen at 50 kilopascals mixed with 1 liter of oxygen at 60 kilopascals, it forms a 1 liter mixture of these gases. What's the resulting pressure? The pressure total is the pressure of nitrogen plus the pressure of oxygen, or pressure of nitrogen, which was 50 kPa. They do have to be the same units when you're adding them up. Most of the time it will be, but just double check and make sure it's given in the same units. So my answer is 110 kilopascals. This is the mixture of the gases. Next one, I have a balloon containing 75 kilopascals nitrogen, 15 kilopascals of oxygen, 5 kilopascals of carbon dioxide, and I have water vapor in there. Total atmospheric pressure is 100 kilopascals. What's the partial pressure of the water? Well, the total pressure we said is the pressure of everything. So pressure of nitrogen plus pressure of oxygen plus pressure of CO2 plus pressure of water, H2O. It says my total is 100 kPa. That's going to be equal to the 75 kPa from nitrogen plus 15 kPa from oxygen plus 5 kPa from carbon dioxide plus whatever the water is. So you can tell you take 100 minus 75 minus 15 minus 5 to get the pressure of the water is 5 kPa for the pressure of the water in the balloon. Now, it seems simple enough. It's not that much more difficult. It's a very good way to use collection of gases. One thing that we need to be aware of is that water will exert a vapor. Water always has a vapor. In fact, any liquid is going to have some kind of vapor above it. If I seal it up in the container, there's this pressure above it, because some of the particles are escaping, and then some are going to hit and collapse into the liquid, and another one is going to escape into the vapor phase. So this pressure it's going to exert anytime I have a liquid. If I were to take the top and open it up, eventually it would all evaporate. Some different liquids evaporate faster than others if I open it up. So this is the vapor pressure above a liquid. Now with water, the vapor pressure, most materials, the vapor pressure does depend on temperature. You can see as the temperature increases, vapor pressure increases. When it reaches 760, this is considered the boiling point. 100 degrees, 760 millimeters of mercury is atmospheric pressure. The vapor pressure table on page 834 can be used to figure out how much water vapor is in the air at any temperature. And I gave you a copy of this on your green sheet. Notice this one I have up here is in millimeters of mercury. Yours has two columns. One has millimeters of mercury, one has kPa. So always when you're looking for these, you're checking the temperature, but you're checking what the units are also. Make sure your units match. So why is this important? Well, as we said, if we're doing a reaction, we want to be able to usually collect the volume, a certain volume of water. So how do we know how much water we actually collected? We have a setup, and I'll show you this in class. If I'm trying to do this reaction, I'm breaking down potassium chlorate into KCl and oxygen. I want to collect the oxygen, so I have this sealed up right here, and I have this tubing. My oxygen is going to run into this bottle, and it's going to fill the bottle up. And I'm going to have some kind of markings on here that tell me how many milliliters I've collected. So I can actually tell what my volume of oxygen is. Now the problem was, we said with a sealed container, there's O2 up here that I've collected. There's also some H2O in there. Because it's a vapor pressure of water, some water is going to escape. So when I'm doing a reaction, I need to get really, really good information. I'm actually going to have to correct for the amount of water that I have. So take a second and write this down. If you're using stoichiometry problems where you're collecting a gas over water, you have to correct for the amount of water. First of all, you have to make sure that the thing you're collecting it in, the container you're collecting it in, is actually has a level of water inside and outside are exactly the same, so the pressures are equal. Then we figure out the water vapor pressure. Get this from the table. We have to know the temperature, so we can get it from the table. And I subtract that from the total pressure. Whatever my total pressure is, now I get the pressure of the dry gas only. Once I have the pressure of the dry gas, I can convert the gas to STP, or I could use stoichiometry to somehow figure out the number of moles. But the most important thing is to get that pressure of the dry gas without the water involved. And then I can do other things with it. So, an example, if you have a gas that was collected over water, 21 degrees Celsius, we'll equalize the water levels and find the volume to be 325 mils. Given that volume of dry gas at STP, the pressure is 102.9. So to figure out the volume of the gas, first step, find out the vapor pressure of water. And this you got from looking up on a table. Next step, calculate the pressure of dry gas. Use Dalton's law. So pressure total, or pressure total minus the pressure of water gives me the pressure of the dry gas. Step 3 lists all the data that I have. I'm given in this problem I'm given T1, I'm given V1, I'm given P1, and I want to convert to STP. I know at STP the temperatures and pressures at STP. Temperature is 0 degrees Celsius, pressure is 1 atmosphere, or 1 atmosphere is 101.325 kPa. 0 degrees Celsius is 273 Kelvin. So I'm going to put those into my equation. P1 V1 over T1 equals P2 V2 over T2, which I've solved right here just for V2. Again, you could put the numbers in first if you wanted to before you solve it. And I get my volume and my volume equation, and calculates out to 299 milliliters. And that's the volume of the dry gas at STP. I can do another problem here. Sometimes I just want to know the pressure of the hydrogen, partial pressure of hydrogen that I'm trying to find. If I have H2 collected over water at 22 degrees Celsius, and I want to figure out what the pressure of the hydrogen that I collected was. Total pressure, again, is hydrogen plus the water. You have to look this up from the table. When I know that I had 22 degrees Celsius, I look up the temperature, the vapor pressure on the table, so I know my pressure of water. And from there, I can calculate pressure of hydrogen is 98.16. Now, once I have this, again, I could go on and find out how many moles I have collected, what the volume is that's corrected, if they gave me more information in the problem. This problem is all they gave us. So tomorrow in class, we're going to go through a couple more problems. We're going to try to see if we can figure these out in class. I'm going to leave these for you to write down right now so you can have these written and ready to go in class. This is, pause your video if you need to for this. And the third one is collecting hydrogen and over water at 22 degrees and figuring out the volume of dry gas at STP. So going a little further than I did with the previous one. So again, pause the video, write these down, and we'll do these in class and show you how these work.